All right, so today we are going to revisit the word problems that we did at the beginning of the unit. So if you recall back at the beginning, we did exponential growth and exponential decay, but we only ever kind of did it in one direction, or we would use a calculator to solve. So now we're going to look at how can you use logs to solve when you're looking for time. Okay, so just as a quick reminder, so our compound interest formula, remember, was A equals P times 1 plus R over N raised to the NT, right? So that's the general formula you're working off of. If you have a situation where it's not compounding interest, then that just means N would be 1, okay? And you just pop that in. That's the easiest way, I think, to kind of remember it. That's how I do it in my head. So let's look at this guy. So you put $1,000 in an account, 4% interest. We want to know how long, so we're looking for time, does it take to reach a balance of $1,500? Okay, so our new balance is $1,500. P, our initial balance, was $1,000. Okay, and then it's 1 plus, and because this doesn't say it's compounding interest, it's just annual interest. So annual interest compounds once a year. So it's going to be 4% divided by 1, so it's just 0.04. And then N, again, would just be 1. It's annual, so that's 1 times a year, right? So annual just means N equals 1. So that's basically just raised to the T power. Okay, great. So we're going to solve this. So I'm going to divide both sides by 1,000. So that's going to give me 1.5 over here, and then it's 1.04 raised to the T power. And then from there, you can either convert, or you could take the log of both sides. So if I take the log of both sides, I'm going to have log of 1.5 equals T times the log of 1.04. So to get T by itself, I will divide. And then I go to my handy dandy calculator, and we type in a log of 1.5 divided by a log of 1.04. And it tells me to the nearest year that it would be 10 years. And there we go. All right, word problem number 2. You put $1,000 into an account, pays 4% interest, but this time we are compounding quarterly. How long will it take to reach 15,000? So basically the exact same problem, but now we're compounding our interest quarterly. So once a year versus 4 times a year, what's the difference going to be? Well, I want to know, I started with 1,000. We want to know when we're going to hit 1,500, excuse me. But now it's going to be 1 plus 0.04 divided by 4 raised to the 40. So first steps will be the same. I'm going to divide both sides by 1,000. That simplifies to 1.01 raised to the 40. Okay, I'm going to take the log of both sides. So I'll have the log of 1.5, and I'm going to go ahead and drop that 4t down at the same time. And then to get the t by itself, you can either do this in 2 steps, divide both sides by log of 1.01, and then afterwards divide by 4. Or you can do it in one big step. So I'm going to, right? You can do it in one big step to get t by itself. And basically I'm putting in my calculator log of 1.5 divided by 4 times the log of 1.01. Okay, so you could do it either way. You just need to be careful that when you put that in your calculator, so log of 1.5 divided by, you need parentheses, because if you don't put the parentheses, then what it's going to do is it's going to divide this log by 4 and then multiply that answer by the other log. And somehow I did not use decimal places, so let me just fix that really quick. And I got to insert another decimal place there. There we go. That sounds better. All right, so in this case, we end up with t equals also 10 years. Okay, so the difference between this problem and this problem, right? When I solved this one, it was like 10.3 versus this one is like 10.2. So is there a difference in time? Yeah. Is it super significant? Okay. All right, next one, same thing, but this time we are compounding continuously. So how is that going to change my problem? So I want to get 1,500 still. I'm still starting with 1,000, but compounding continuously, that's a PERT, right? Final amount equals initial amount times e to the rate times time. So this one's set up just a little bit different. We're going to solve the same way though. Divide both sides. I'm going to get 1.5. And then here, instead of taking the log of both sides, I'm going to take the ln of both sides, because anytime you have a base e, you always take an ln. And since I know the ln of e cancels, I'm just going to go ahead and write that. So then I'm just going to take that, divide both sides by 0.04. So I'm doing the ln of 1.5 divided by 0.04, and that is 10.1. So again, 10 years, right? So the difference between these is not crazy different, right? Quarterly versus continuously. It definitely makes a difference, right? But like we talked about before, it makes less of a difference the more times you compound. Those first few compoundings make a really big difference, but when you start breaking it down more and more, it doesn't make all that big of a difference. All right, next one. So switching veins a little bit. So this time we are looking at a decay function. So radioactive material decays 15% per day. You have 50 grams at the beginning. How long until half of it is gone? Round to the nearest tenth of a day. So if we started with 50 and we want half of it to be gone, that means I'm going to be left with 25, right? Okay, and the only difference for decay, remember, it's the initial amount and then it's times 1 minus your rate, right? Raised to the time. Okay, so you can use this same formula except with subtraction, and we don't really talk about compounding decay, right? We really just kind of talk about either continuous decay or regular old decay. Cool, so I'm going to solve this. I'm going to divide both sides by 50, so that's going to work out to a half. I don't know why I wrote a half instead of 0.5, but there you go. That would be 0.85 to the t. And I'm going to take the log of both sides. So I'm going to have the log of 0.5 equals dropping that exponent at the same time. And then I'm going to divide both sides. So I'm going to have log of 0.5 divided by, so log of 0.5 divided by the log of 0.85. And again, make sure you recognize the difference. You can't do log of 0.5 divided by 0.85. You have to have both logs, and watch out for your parentheses. So that works out to about 4.3 days. So it takes about 4 days for half of that substance to be gone, which is pretty quick. Okay, uno más. All right, 100 grams of radium are stored in a container. The amount of radium present after T years can be modeled by this equation. I love it when they give me an equation. That just means less work for me. How many years, after how many years will only 5 grams be present? Well, they said R, capital R, is the amount present. So I am plugging this in for capital R. So it's going to be 5 equals 100 times e to the negative point, and then I think it's 3 zeros for 3t. Cool, so I'm going to divide both sides by 100. So that'll be 0.05 equals e to the negative weird decimal t. Because it's a base e, I'm going to take an ln, right? So the ln of 0.05. And then over on this side, the ln of e cancels, right? Because the log base e of e, and that cancels out. So that's going to leave me with just negative 0.004, 3 zeros. And then I'll divide both sides to get t by itself. So in my calculator, I'm doing the ln of 0.05 divided by negative 0.00043. So that is 6966.8 years. Okay, so kind of a comparison between the two, right? This one, half of it's gone after 4 days. But this one, right, when we take a look at this, it's going to take, almost 7,000 years, right, to go from 100 grams down to 5. So that's the kind of the danger in radiation. And there we go. Okay, so that's how you'd use a log when you're dealing with a word problem to solve an equation. It's not too bad. It's really just tying together some stuff we've already done.